Yes, so Antoine is a student at EPFL, working with Guillaume Dahl. Antoine, take it away.
Okay, so hi everyone. Uh, During the last semester, I've been working with Leon as well as a few other people from KFL on a framework to do GraphBLAS and Sparse Computation with GQ acceleration. And I'm happy to be here to end up show how we progressed as well as share some of the learning opportunities that we had along the way. So to begin with, I'm gonna start about you by introducing GraphBLAS because I'm not sure everyone feels familiar with this. So GraphBLAS is an API specification that tends to define building blocks to express graph algorithm of graph in our case in the language of linear algebra. And it uses the equivalence relationship between a graph and then this graph CG extension matrix. So as a basic example, we can see here that if we have a vector with a one bucket encoding to indicate the single vertex, and we multiply this vector by the graph's adjacency matrix, we get in the output the two vectors that are neighbors of the original two vertices that are neighbors of the original vertex. So just see one example of you can find the neighbors of a vertex just doing the sparse matrix vector modification. There's in fact a lot more one can do using the sparse matrix vector multiplication. For example, if we have a set of vertices indicated by one function cutting the vector, and you multiply this by the adjacency matrix, we can count the number of facts from our original set to every other vertex in the graph. And the main twist with GraphBLAS is the use of usually defined semistrings or semiring, and to make it quick, is a set of two binary operators. The first one, which is the multiplication that we're going to use instead of the original multiplication. So that when you multiply a vector by a matrix, we need to multiply each element of the vector with an element corresponding to the matrix, and then add them all along their column together. What we want to do is we want to do the same computation exactly, but with the twist that we want to use any binary operator instead of binary multiplication and addition. And this gives us a lot of bracket power. For a second example, if we use the addition operator instead of the multiplication, and then the mean operator instead of the addition, it's complicated, and we do this on a weighted graph, we can see that this is equivalent to finding the shortest path from the given set of vertices to others in the graph. So it's a bit abstract, but the main idea is that we want to be able to use a single operation, which is matrix vector multiplication, but with supplying any binary operator that we want instead of the regular addition and multiplication. This is already perform a very wide variety of operations on the graph. And while we read this, we encountered a few challenges. The first one is that we have a very high memory to computation ratio. So for those not familiar with GPUs have very large computing capacity with thousands of parallel threads. However, they all share the same memory. And when working with sparse matrix vector multiplication, every bit, every number that we read from memory in the matrix is only going to be used once in the multiplication. So here you have the another compressed password format. And when we're doing matrix vector multiplication, we're going to be reading the entire sparse matrix once and using each number to be one multiplication with any number that we want, and then one addition, and that's all. So it's very easy for us to be bottlenecked by the GPU's number bandwidth. And the second challenge in the cartography is that we can have trouble with load balancing. So when using the CSL format, the most basic way to perform the matrix vector multiplication is to assign one thread to each row of the matrix. However, if some rows have significantly more values than others, then we are going to have a GPU spend a lot of time in a single row with a single thread assigned to it, and all the other threads are going to be stalled. And once again, they're not going to be able to use the entirety of the GPU's large computing capacity. And this is the idea. The third problem that we encounter, but as we can see, have a very nice solution for, is modularity. So as I've said just before, and then we need to be able to perform the matrix vector multiplication with any combination of two operators that we know, and there is a few thousand binary operators that are defined as the GraphBLAS standard, so even more combination of those. So it's not really feasible to implement customized symbols with no level for each combination of operators. So we're gonna use a little trickery here to help us. So we have these solutions to these quarters. The first two problems can mostly be fixed by the storage formats. So the high memory and load balancing, they can be partially resolved by using better storage formats. And one nice thing is that this does not really depend on the GPU architecture, and there has been a lot of research to find better, more optimized storage format for parallel execution. However, the bad news is that all this research has concluded that there is not one single perfect storage format for sparse matrices, and the best format will always depend on the specificities and the topology of the matrix that we're considering. So that's a bit of a shame. On the third problem, we used a very nice package from the Julia GPU the Julia GPU ecosystem, but is on the I'll put a typo here, sorry, which is kernel fractions.gl. Which we can file it, so yeah, it's written correctly. So kernel abstractions.gl, as its name indicates, adds a layer of expression to GPU kernels. In general, whenever we're working in GPU and GPU kernels, we will hack a lot of modularity. The GPU kernels are in general not a functional programming language, so it can be hard to have this kind of composability, everything that we would want to make this easy. However, this is provided to us by kernel abstractions here. On the left, you can see that we're able to define our sparse matrix vector multiplication kernel by giving as parameters to functions. Here, the move and add parameters can be any Julia functions that have the appropriate number of parameters. And just like this is only basically to implement the sparse matrix vector multiplication according to the GraphBLAS standard. The magic here happens with just-in-time updation. So basically, anytime you will multiply a matrix and a binder with a new set of binary operators, kernel abstractions is going to compile a low-level kernel with these two operators basically hardwired inside it. And this is this allows us to write a single high-level kernel with parameters, and kernel abstractions is going to generate every combination of operators that the users would possibly want. This is also used by NVIDIA commercially, the Sparse library. It's a compilation, but it's in my opinion, it's not as easy to use as refers users to manually write the code that they want to use as binary operators and strings, and then compile them manually and then feed them to the camera. And here we get a very nice integration with the rest of the Julia ecosystem, or you just give any function as parameter and the kernel abstraction, but is able to eat the rest of the run for us. So finally, I'm gonna share a few benchmarks and a few results. This is all in very early stage, so it's important to keep it in mind. We compared how sparse matrix vector multiplication against the Julia Sparse library, that's called the standard library. And we can see that when we are using a compressed sparse real format, we are able to get about 1 order of magnitude faster than the Julia Sparse library. And the NVIDIA's Sparse library is another order of magnitude faster. We tried a second storage format that is rather to work more better on the GPUs or the memory users that I mentioned earlier, which is the SPLS storage format, which the people sorted on the left. And you can see that this storage format with our auto notation was able to get performances that were close to Q-sparse or compressed sparse raw formats. And unfortunately, we weren't able to test against Q-sparse's SEL format because it's not yet implemented together GR, so with the riders. And finally, we tried to do some GraphBLAS search, which is a very common graph analytics algorithm. And we benchmarked it against GraphGR as well as the RSA GraphBLAS search evaluated with linear algebra using strict force GraphBLAS. And here we were able to get very promising results. This is tested on the randomly generated graphs. And yeah, we can see that we get not only faster runtime, but also a better scaling as the graph size grows. All right, so I think I'm out of time. Thank you for listening. Happy to take any questions.
Does anyone have any questions for Antoine? I'll like repeat them here if it's, you know, audio is complicated. Go ahead.
A very quick question. Just are there any insights about how to adapt GraphBLAS for Julia or like designing
Yeah.
specific interface today?
Antoine, did you hear the question? Okay. The question was, do you have any insights on how you might adapt GraphBLAS for Julia, or the experience of adapting GraphBLAS for Julia throughout your project?
Well, so I don't know what kind of insight you're looking for. I would say the biggest part was to set up the Consequently data structures and stuff like this to in the correct ways to integrate correctly with all the rest of the Julia ecosystem in the stat parameters and stuff like this. As I showed in this slide right here, the mitral computation. I mean, it's a bit more complicated than what I'm showing here, but it's otherwise quite simple. So most of the work was also trying to find data storage format that would work well with most matrices and GPUs, which is when we support the ACL.
Great. Does anyone have any other questions? I ran a little long on mine and mine up next. So if you have any other questions, I think we have time for one more. Okay. Let's thank our speaker.